A frozen star. Sounds like some kind of oxymoron, but what if they are possible? Not now, but in the distant future. Despite how vast and possibly even infinite the universe is, its stellar population might not seem all that diverse. If we're talking specifically about stars on the main sequence. It's kinda like in this image. Here we have a ball mostly made of hydrogen. Here's another, but bigger, hotter, and slightly different color. And over here, it is smaller and cooler. Fascinating. But, of course, I'm exaggerating. I don't really think that way, and I don't think most of you do either. I made an important clarification. Stars on the main sequence. That is the main stage of a star's life during which they are stable and don't change significantly. But if we add evolved stars at various stages, stellar remnants, white dwarfs, neutron stars and black holes, then it all becomes more diverse and even more interesting, and this is only considering the objects whose existence we are sure of, or almost sure of. But what if, in the universe, there exist objects we are not even aware of? Or we do suspect that some weird objects might exist and even theorize about their properties, but we haven't found them yet. And this is where theorists can really let their imaginations run wild. Scientists have described quite a few stellar objects that could in theory exist. Some of them might seem downright fantastical, like boson stars that could be transparent or stars made of dark matter or dark energy. We still don't fully understand what dark matter and dark energy are, yet we are already coming up with objects made from them. But not all hypothetical objects are the same. There are degrees of hypotheticalness. Well, take for example black dwarfs. Let's say white holes and black dwarfs are both hypothetical objects, but the situations are very different. White holes probably don't exist at all, but black dwarfs could very well be a natural product of stellar evolution, and the reason we don't observe them yet is simply because it's still too early for them to appear. The universe is too young, and if we were to travel to the distant, well, very distant future, it is highly likely that we would find black dwarfs. And today I want to talk about such objects, currently hypothetical but ones that don't require new physics or poorly understood substances. These objects, based on our current understanding of physics, could very well exist, but in the future. I'll talk about 3 such objects. About the seemingly paradoxical blue dwarfs, iron stars, and frozen stars. It seems that in the distant future the universe will be a completely different, unrecognizable place. I'm Andrei, and this is Cosmos Elementary. Why did I say that blue dwarfs seem paradoxical? It is possible that for those of you who have some understanding of how a stellar mass and color are related to its temperature, the phrase blue dwarf might have sounded strange. Typically, blue stars on the main sequence are the most massive. Smaller stars are white, even smaller ones are yellow, then orange, and further along they become redder. This is the general idea. Right now we're not talking about, let's say, white dwarfs, because they are stellar remnants. It's worth reminding that when we say a red dwarf, it doesn't mean that we would see it as bright red with our own eyes like they are often depicted in illustrations. Just like our sun. Even though it is called a yellow dwarf, to our eyes in space it appears white. Color here is also a manifestation of temperature. If you heat metal, it first turns orange, then yellow at a higher temperature, followed by white, and so on. Here's a table which gives us some idea of what stars of different classes would look like in terms of color to our eye. The red M dwarfs are at the bottom, and they actually appear orange rather than red, but they are definitely redder than the massive blue stars. More massive stars are hotter and blue, and another important consequence of all this, especially for us right now, is how lifespan depends on mass. Why am I emphasizing this? The thing is that blue dwarfs are red dwarfs. Huh? Yes, it's quite likely that in the distant future, red dwarfs could become blue. Sun-like stars become red giants, but here it's the opposite. To understand why this might happen and why there is such a difference, we need to look into some peculiarities of these stars. When I talked about the small diversity among main sequence stars and how they mainly differ in mass, color, and temperature, that was slightly misleading. Or maybe not slightly. And I'm not even talking about other aspects that make stars different, such as their chemical composition, what generation they belong to, or the systems they are in, all of which can also influence the properties and evolution of stars. The basic difference in mass leads to not only differences in the appearance of stars and their lifespan, but also in what happens beneath the surface of stars and how they change throughout their life. I recently made a video about the internal structure of the Sun, how there's the core at the center where nuclear fusion occurs, followed by the radiative zone, then the convective zone, and then the outer layers. And stars with different masses can have a different internal structure, and this leads to significant differences in the star's behavior and its evolution. I've already mentioned the difference in their lifespans. During their life on the main sequence, stars are in a constant struggle. Gravity tries to compress the star to make it collapse, but this same gravity creates conditions in the core with such temperature and pressure that nuclear fusion reactions begin, producing energy and radiation. And this creates an outward pressure that counteracts gravity. As long as one force balances the other, the star remains in hydrostatic equilibrium. It neither collapses nor blows apart. It can stay in hydrostatic equilibrium as long as it has what is often referred to as a fuel for nuclear reactions, that is, hydrogen in the core, which through a series of nuclear fusion reactions is converted into helium. It makes sense to think that a star with a greater mass has more fuel. And that's true, but then shouldn't they live longer? Well, if it weren't for gravity, you heartless thing. The problem is that a greater mass creates conditions in the core where nuclear fusion reactions occur more intensely. And even though there is more fuel, it gets used up much faster, and consequently it runs out more quickly. This is a simple calculator that we can use to estimate an approximate lifespan of a star on the main sequence, depending on its mass. If we input a value of one solar mass here, we'll get a predictable result 10 billion years. You've probably heard that the Sun is expected to live on the main sequence for that long. If we set it to 3 solar masses, the star's lifespan decreases drastically to about 642 million years. A star with 10 solar masses will live only 32 million years. For a very massive star with 100 solar masses, the calculator shows a lifespan of just 100,000 years. But what happens if we go in the opposite direction? The term red dwarf is often used to refer to stars with a mass ranging from 7 to 8% to 50% of the solar mass. A star with half the mass of the Sun will live over 5 times longer than the Sun. 2/10 of the solar mass, 559 billion years. And the lower limit of 0.08 solar masses for red dwarfs gives a lifespan of 5.5 trillion years, according to this calculator. Of course, this is a very rough calculator that doesn't take many parameters into account. It's more of a tool to give a general idea. There are estimates that the lifespan of the least massive star could reach up to 10 trillion years. That's over 700 times the current age of the universe. These values are hard to wrap your head around, but even the most massive stars classified as red dwarfs live several times longer than the current age of the universe. And while we do see more massive stars dying, in the case of red dwarfs, not a single star of this type had time to die a natural death, using up its fuel reserves since the beginning of the universe. They haven't even lived a quarter of their lifespan yet. So once again, the evolution of stars like the Sun or even more massive stars we can not only model and theoretically predict, but also observe these stars at different stages of evolution, from formation to death. This means that we have a pretty good understanding of what happens with these stars throughout their entire lives. But in the case of red dwarfs, at best we can observe their youth. Therefore, there is much more unknown about them. And yet they are the most common type of stars in our galaxy. So we have to rely on theoretical calculations and models for now. And this is why blue dwarfs are hypothetical objects. Red dwarfs can become blue at the end of their lives. And so much time hasn't passed yet. The universe is just too young for this to have happened. What happens to a solar mass star when the hydrogen in its core runs out? It inflates and becomes the red giant. Almost all of the hydrogen in the core, which occupies less than 1% of the Sun's total volume, runs out, leaving behind the products of reactions, helium. But the core of a star, with the mass of the Sun, isn't yet hot enough to initiate helium fusion reactions. Therefore, nuclear fusion reactions come to an end. And what does this mean? It means that without fusion reactions in the core, no pressure is generated to push outward, and nothing counteracts gravity. As a result, the star begins to contract. But I just said it expands. But that's only the first step. In general, as the star contracts, the temperature in its center rises again, and nuclear fusion reactions start occurring not in the helium core but in the next shell surrounding it. And the thing is, this shell is much larger in volume than the core was. A lot more energy is released, creating a much stronger radiation pressure. Now gravity loses the battle and the star begins to expand. Meanwhile, the surface temperature decreases, and as a result, the star not only grows in size but also becomes redder. And that's how you get a red giant. Red dwarfs have a different story. Specifically, we're talking about stars with masses less than 20–25% of the Sun's mass. Remember I mentioned that stars with different masses also have different internal structure. For the Sun, after the core, there is a radiative zone followed by a convective zone, where the material actively moves closer to the surface. In a lower mass star, right after the core, a convective zone begins. This means that the material is actively mixed, and large composition gradients like those in Sun-like stars do not form. This allows a significant portion of the hydrogen in the entire star to be used up, not just the hydrogen in the core. As hydrogen gets used up, instead of expanding and becoming redder, the star remains small, but its surface temperature rises. This means that its color shifts towards blue. They probably won't become as intensely blue as O-type stars, but they will no longer be the red dwarfs we know. For billions, if not trillions of years, they will continue to turn bluer and bluer. And eventually, without going into the red giant phase, they will become white dwarfs where thermonuclear reactions will no longer occur. They will continue to cool down, and according to, rough estimates, in a quadrillion years or so, they will become black dwarfs. By the way, the term blue dwarf is applied to two different objects. To the stage of red dwarf evolution that I just described, and also to blue dwarf galaxies. Which didn't help me when I was searching for information. The astrophysical database kept giving me results about galaxies. The story is somewhat similar with our second hero, the iron star. The term iron star is sometimes applied to certain representatives of the luminous blue variable stars. Their emission spectrum is characterized by strong iron lines, but these are not hypothetical stars. They are quite observable. Today, however, we're talking about different iron stars. Literally giant spheres of stellar mass composed of iron. Iron stars of this kind were described not by just anyone, but the Freeman Dyson himself in his 1979 paper. Many of you may recognize this name from Dyson spheres, hypothetical objects of artificial origin, but in fact he worked in areas such as quantum mechanics, quantum field theory, nuclear physics, and is one of the founders of quantum electrodynamics, and so on and so forth. In this paper, he describes the possible evolution of the universe and the matter within it in the distant future. There is a section titled "All Matter Decays to Iron." Here he describes a scenario in which, after enough time has passed, elements heavier than iron, as a result of various processes, decay into stable isotope of iron. Elements that are lighter than iron are gradually converted into it through synthesis reactions. And after a very long period of time, most of the ordinary matter in the universe will transform into iron, including that found in long-lived stellar remnants like white dwarfs, for example, as a result of quantum tunneling. And over time, these remnants would turn into cold iron spheres. It would certainly be fascinating to observe such objects, though we would probably need some very strong light source, as they would likely travel through the universe almost in complete darkness. How much time is needed for the formation of these stars? A very long time. Well, 100 million years? Or maybe a trillion years? Well, compared to the Dyson's estimate in his paper, even this is just a brief moment. He writes that for this to happen, 10 to the power of 1,500 years must pass. That's a 1 followed by 1,500 zeros. So we won't get to walk on the surface of iron stars. Even if we somehow could, considering that it would be rather difficult due to the extreme surface gravity. Interestingly, this is not the end, and Dyson writes that these iron stars could eventually collapse into neutron stars or black holes. And an important caveat. Some of you may have noticed the title of Freeman's paper. He describes all this for a so-called open universe, or the universe with an open geometry. And we do not know for certain if it is. And now scientists believe that flat geometry of the universe is more likely, considering what we know now. Frozen stars might seem like the strangest type of hypothetical stars in my today's lineup. The word star is associated with an incredibly bright and hot object, and yet frozen stars could technically still be called stars because thermonuclear reactions might occur in their core. At the same time, they are so cold that ice could form on their surface. On the other hand, we already have objects that in some way resemble frozen stars. If anyone has an idea of what I'm talking about, you can pause the video and type your answer in the comments. Now let's see if you were right. Of course, I'm talking about brown dwarfs. They are something between stars and planets, and limited thermonuclear reactions can even occur within them. I already mentioned today that the minimum mass limit for the least massive stars, red dwarfs, and thus for stars in general, is approximately 8% of the solar mass. This is roughly equivalent to 84 Jupiter masses. And brown dwarfs are objects whose masses range from 10 to approximately 80 Jupiter masses. Of course, it's not just mass that plays a role, but also factors like composition. However, in general, with less than about 80 Jupiter masses, an object can no longer sustain consistent thermonuclear reactions in its core and is not considered a star. Consequently, the surface of such objects like brown dwarfs can be relatively cold. For instance, the temperature of this brown dwarf observed by the now retired Spitzer infrared telescope was estimated to range from -48 to -13 degrees Celsius. However, in this case, it's not all that surprising. The object is much closer to a planet than to a star, with a maximum mass of 10 Jupiter masses, and possibly even less. Since energy cannot be generated through thermonuclear reactions in its core, it shouldn't really shock us that it's that cold. It also seems to be traveling on its own through the galaxy. It doesn't even have a stellar companion to warm it up. But what if in the distant future of the universe, something changes and thermonuclear reactions can start occurring in less massive objects with lower temperatures? This is where the concept of frozen stars come into play. The possibility of existence of these hypothetical objects is described in a paper by Fred Adams and Gregory Laughlin. All of today's stories share the fact that tremendous amount of time must pass for these objects to come into existence. The same goes for frozen stars. If they do appear, it will only be after trillions and trillions of years. The universe has inevitably been changing since its beginning, and this includes the chemical composition of the universe. Let me remind you that at the very beginning, there was almost no chemical diversity. It was mostly hydrogen, helium, along with a few isotopes and lithium. Heavier elements began to appear later through various processes, mostly associated with stars. In thermonuclear reactions in their cores, in supernova explosions, in stellar mergers, and so on. Over time, the parameter known as metallicity increases in the universe. As you might remember, astronomers refer to all elements heavier than hydrogen and helium as metals. And roughly speaking, the higher the proportion of metals, the higher the metallicity. Typically, the older a star is, the lower its metallicity, and the later it formed, the higher its metallicity. Although, of course, there can be various mechanisms of contamination as well. In general, the universe is slowly but steadily transforming lighter elements into heavier ones, and their abundance will continue to rise. Adams and Laughlin suggest that this could lead to the following. Higher metallicity leads to more efficient cooling, which in turn could mean that even more low-mass stars will form in the future than we see now. What is even more interesting is that they write that such metallicity could lower the minimum mass threshold for stars required to sustain thermonuclear reactions, and this is related to opacity effects. Opacity is one of the important parameters for stars. For example, high opacity can more effectively retain energy in a star's interior by preventing photons from escaping. With the metallicity several times higher than the Sun's, stars could form with as little as 4% of the solar mass. In these stars, thermonuclear reactions could still occur in the core, but the surface of such small stars could be very cold, around 0 degrees Celsius. Ice clouds could even form in the atmospheres of these strange stars. These frozen stars would be very faint and would likely resemble brown dwarfs in appearance. Additionally, they could form from the merger of two brown dwarfs. So, as I said, such an object is both strange and not that strange at the same time. It's a shame, of course, that we won't be able to physically observe them, unless, of course, someone invents a time machine capable of traveling trillions of years into the future. Then we could witness very strange objects in the universe, very different from our current one. Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye.